Welcome to our lectures on the DC microgrid and the control system. Today we shall visit the different control techniques specifically applied to the DC microgrid system. We intentionally talked about the microgrid in general in our field lectures and its control, and then only so that student can derive what are the differences in the DC microgrid. So, as we know that in case of the AC microgrid, we have a PQ control and the VYF control, and essentially it leads to the voltage and the frequency control of the two quantities. And generally what happens in microgrid, when it goes to the islanding mode to manage its demand, frequency drooping will be there, and with that they generally also changes the voltage, and thus they wanted to maintain the VYF control. And in an AC generator, frequency can be controlled through increasing or decreasing the mechanical input power. So, that is easily possible, because once you want, because ultimately you know that once you want to increase the real power, then you have to increase the mechanical input. Once you want to change these excitations, and so that you can control the Q, you will change the excitation. So, by changing the excitation you control the voltage, by changing the mechanical input you control the frequency, and thus that will be reflected in the change in the real power. The voltage is controlled by injecting or absorbing the reactive power. Same thing it will be required to do it with the switching solutions. The STATCOM can be, or the, since it is a microgrid, it can be a shunt active power filter, can mimic these characteristics. So, the DC system, it has only one voltage, so there is no frequency. Voltage is unique quantity and that required to be controlled. So, you do not have a separate control like your frequency and the voltage, you just have a voltage control, and there is no concept of the reactive power there as it is. So, DC voltage can be controlled by injecting power to the DC network, and it can also take out power from the DC network. So, that control has to be managed, and ultimately what you have seen, the frequency control, that frequency changes while it is increasing the demand, you will find that voltage, bus voltage will droop, and we require to control the droop. So, that is the basic essence of the DC microgrid. We can assume that all the generator and the loads are interfaced to the DC network through individual converters. So, of course, their bus voltage, and there can be a little bit of mismatch between the input of this particular load, and for this reason, for example, if you are charging a laptop, so it is 18 volt, if you are charging a mobile, it is a 5 volt. So, you have to put a laptop charger, you have to provide a mobile charger, accordingly its output voltage may be different. So, the summation of the converter power must always be 0. So, that is something that we want to make it as axioms, that the summation of all the converters power must be equal to 0. Therefore, the effective voltage control in the DC network should continuously monitor the power balance accordingly. So, it has to, over a period of time, it may be at in transient time. So, you maybe have a exchange of power from the one converter, and ultimately it will feed it back. So, if there is a huge load change, of course, your battery cannot pump that much of huge amount of current instantaneously. So, voltage will drop. With a subsequent time, that bidirectional DC to DC converter from the battery will restore the bus voltage, that is the one of the requirement. So, thus if you, in terms of the mathematics, you put it like that, the summation of all the converter power must always be 0. So, therefore, an effective power control of the DC network should continuously monitor the power balance and accordingly send the appropriate control signal to the related network component, for example, converter, generators and the loads. The paralleling of the power sources in microgrid application through the power electronics modules offers number of advantages. We have told in several times in the introductory classes that this power converters is it can have a number of converter over the utilization of the single high power converter. If you have a multiple converter, then you have your topology will be different. Generally, depending on the topology, you choose the DC to DC converter, isolated DC to DC converters. And in general, what happen if you have so many small DC to DC converter, all the efficiency will be less because you cannot put huge amount of money to investigate or reduce the losses of the particular DC to DC converter. But if you have a centralized DC to DC converter which have a multiple output, that is preferred over a multiple DC to DC converter. And thus, you have two different method of control. What we have seen also in case of the microgrid also in AC microgrid, there is a master slave control. One will be the master, other will be the following the instructions. Another you have a frequency control you had in a microgrid, AC microgrid, and here you have a voltage droop control. That is the difference. Now, master slave control will be almost the same thing what we have discussed in our previous class in case of the AC microgrid. So, master slave control essentially you have a DC bus and this is the master. Task of the master to set the DC bus voltage according to the load condition. If it is 48 volt, then you have a little bit of tolerance. So, if load is little bit increasing, it can push up, it take down the voltage little bit, maybe 46 volt or some amount of tolerance, and accordingly this converter will adjust themselves. So, and the power and if you have a constant power load CPLD, then accordingly it will adjust. Otherwise, the power consumption will decrease also, because V square by R all you have a parallel connection. If the bus voltage decrease, then you have a little bit of change of the consumption pattern, and in that way you save the power. But problem lies with the constant power load. If you decrease the bus voltage, then it will track more amount of current, things will be lossy. So, you have to have a little bit of more control on the constant power loading. So, in this configuration each block is composed of the DC source, a static converter and its controller. So, this is the control. We require the control because we may have some entities are constant power. So, let us describe these blocks. The first block of the first block itself is the master block. The controls the grid voltage, while the other block slaves controls the current. So, that is what it is saying. If it is CPLD, then if you have a droop, voltage has decreased. So, you have to increase the current, and some way or other if you have a different kind of loading pattern, then you can control the current so that your consumption pattern may be reduced, and accordingly you can change. This control scheme has an disadvantage, needing fast communication channel, because once load change occurs, DC is transient phenomena while quite severe. So, it does not have a zero crossing, it is a step change. So, please for this reason all the changes are quite severe, and to take care of that high speed of the transient, you require to essentially have a very high speed communication channel. That is one of the major drawback of the DC microgrid, that your communication channel required to have a very high bandwidth, since the reference current for the slave converter are provided by the master block. So, if it is a switching frequency at 10 kilohertz, then you have to have that information to be fed to the next switching cycle. That means the data to be transferred within a 100 microsecond. Another control is a droop control. So, that is quite familiar control here. What we have done this as this taken from this the same control in the AC microgrid or overall grid system while when your frequency drops and all those things. Here figure 2, this is a figure 2, this is schematic diagram of the droop control, shows the block diagram of the voltage control scheme. Each droop control emulates an independence behavior reducing the converter output voltage with the increasing the supplied current. So, this is something we require to understand. So, that occurs once your loads are constant power load. Otherwise, you will be happy if your little illumination is decreased in your light. So, there is not much problem, but you can save power in that way. You can also have a energy saving once your demand is more. So, this is the load and ultimately these are the different kind of source and all will generate the current to maintain the DC bus voltage up to a level of tolerance. And this strategy promotes the current sharing. So, this is something like your parallel operation of alternator which you have studied in your BTech classes in second year or third year. So, the strategy promotes the current sharing between the parallel converters connected in the DC microgrid without the need of the central control. That is quite understandable. The control method avoids dependency on a single power converter. If master controller goes out, then it is a total blank, you do not have any redundancy. But here in this case you have a huge redundancy. So, whosoever can take care of the load, it will take care of the load. If some, because there is no concept of the pilot generator which will fix up the frequency of the system, because generally what happen in your transmission line, normal transmission line, not a microgrid. So, biggest generator generally asks to set out the frequency and rest will synchronize with it. And in case of the microgrid, there is no concept of the biggest generator, and that if wind is more, then wind will be the sole contributor, and if solar is more, solar will be more sole contributor. In absence of the solar and grid, maybe the energy resources like battery are the sole contributor. And ultimately whosoever has a capability to handle, they will handle. That is the automatic shading. Once if solar irradiation is more, then it will take the lead to control the drooping, and ultimately all the bus will be asked to meet that voltage, all the converter. So, that is quite phenomenal advantage. So, that what happen, that will help you to share the burden of the individual converter. What happen, maybe at 12 noon the solar is in at peak and thus it is generating maximum amount of energy, then solar converter is fully loaded, and that time maybe that bidirectional DC to DC converter is even idle, it is, or maybe a small amount of power is transmitting from the bus to the battery. And think about that the case at a 6 p.m. evening, maybe that is generally in evening wind picks up. So, what happen, wind will try to flow, but main chunk of the power will come from the battery, and ultimately task of this maintenance of the DC bus will be delivered by this actually bidirectional DC to DC converter, which is charging and discharging the battery. So, thus what happen, the loading of the converter become optimally, and one converter is not loaded throughout the period of time. So, that is one of the biggest advantage of the voltage droop control. That is what it is stated, and this method the voltage control is shared among the multiple converter that are located at the various buses of the network, and also it has got excellent relaxation time. The control of the DC distribution network is directly related to interfacing control interfacing converter control. Several control approach for voltage source converter have been proposed in the literatures. The most common are the, definitely will come little later, that is the vector current control and the power angle control. So, we have both those topics we have touched in a AC microgrid. We shall see that what are the little variation here, because you do not have any concept of the voltage angle control in case of the, but you may have some sources AC to DC, like if you are grid connected, your entry point to the active rectifier and also wind. So, let us discuss it. The principle of the power angle control is fairly straightforward. Why it is so? The active power is controlled, you know that P equal to V1 V2 by X sin delta. This is the relation, and thus where V1 is a sending end voltage, V2 is the receiving end voltage, and X is the impedance, and sin delta is a angle between this V1 and V2. Thus, what happened? The active power is controlled by the phase angle between the VAC and the AC system. So, if you want to send power, you change this angle within 0 to 90 degree. The challenge is that if it is a short transmission line, generally phase angle is very less. And while the reactive power is controlled by varying the VAC voltage magnitude. So, generally the same thing we have done in case of the rotating solutions. The main disadvantage of the control technique is that the control system cannot limit the current flow within the converter, because ultimately what happen, once you are increasing the power, then essentially you are not changing the voltage, and thus we are changing the current. So, it has a limitations of the flow of current, ultimately it will be restricted by the protective devices. So, you have a limitations of the power change. On the other hand, if you have a direct vector current control, that is a direct control method, and the current control technique is approached, we have a average or the peak current control, and in this method, and it can be limited the flowing current between the two converter during the disturbance. So, you fix out that this because bus voltage is fixed, that is something you require to do that, and while doing it you can fit maximum 15 ampere of the current, that is your rating. So, that has an advantage, because you are inherently protecting from the short circuit condition. Protection is a very big issue in the microgrid, in DC microgrid, because you do not have a problem, you have a huge problem related to your short circuit, because you do not have natural zero crossing, and apart from that, absence of the inductance that makes the system very fast, and transients has a very detrimental effect on this DC microgrid. And in this method, the 3 phase voltage and current of the converter is transformed into the rotating DQ frame once you are converting the AC to DC to fit into the DC microgrid. This transfer quantity is synchronized to the AC grid voltage by using a phase lock loop. So, you will generate the you will convert into the AC to DC, and this will maintain the phase lock loop. We shall discuss it here. So, this is the point of common coupling, and there is a little change here, because with the, and we assume that there is a sufficient amount of the RT, terminal resistance. Generally terminal resistance is neglected. While writing the power flow equations, there was no mention of the resistance, but in a microgrid I have told you, please visit our, I think, lecture number 3 or 4. So, we have discussed in detail what are the changes of the normal grid and the microgrid. So, resistance plays a huge role in case of the microgrid, and thus you have a PWM converter and you got a DC bus, and it may be from the grid or it may be from the other AC sources, for example, the wind. So, the general architectures of the voltage control vector control of the voltage source converter. Now, what happen if you have a problem of the DC bus, then you will have a DC bus control. You require to maintain the DC bus voltage generally around 20% higher than the rectified voltage, because you have a this is a bidirectional switch. Even if you withdraw the pulses of the PWM, you will get some voltage here. That will be the 3 phase rectified voltage, 6 pulse voltage you will get 3√3 Vm by pi. So, this kind of expression you will get. So, you have to take it above 20% by switching, because essentially it sees a boost converter in it if you see through that side. So, you require to maintain the voltage, that is the Vref is generally 20% higher, and now you will once you maintain it is just like the synonymous will be the controlling the excitation of your synchronous generator. So, visualize is a static solution of your synchronous generator, but it converts also AC to DC. So, you have a P. Now, next thing is that you require to control the power, because you will take this is the infinite source of sink, your grid, assume that. So, you should not take you take that amount of power which is has been required by the load, how you control it also. So, generally what happens, so you have a this power reference you will be calculating and will compare it, and accordingly you will actually generate, and this will be fed to the PI controller, and these two controller current will add up, since this will be a DC quantity in a rotating frame, and thus you get the ID reference. Same way you will have a Q reference, and the because you may not allow to take the current at unity power factor, you may be allowed to take the current is some power factor prescribed by you. So, you may be penalized for doing that, and for this reasons you will have that issues also. So, moreover you may require a droop control, and that comes into the pictures once you have see that it can switch over. Generally you can have a you cannot have IQ rep to compensate both your sag, ultimately this will come into the picture, generally it does not come into the picture in a normal healthy condition. If you have a sags and soil, then only this comes into the picture, that is a AC reference and PI controller, ultimately this will affects your reacting component of the power. So, accordingly it will affect, then you can also definitely once you have a transient sags and soil, definitely this operation required to be off. Similarly, once you are maintaining a DC bus voltage first, that is your first task, and then only you will go for the controlling the current, and it may be time shared also, time division multiplexing. So, this switch sometime will maintain the DC bus voltage, and then it will sometime will help you to restore the reactive power, and same way this also possible. And then you have got a inner current loop, and that has to be very fast, and that is operating near close to the switching frequency. And thus what will happen, so you got a PL, so you got then you convert into the DQ to the ABC frame, ultimately from the PLL you generate theta, and that logic you fit to the PWM, and again what theta you are getting you can reconvert it to the ABC to DQ, and also you can compare what current you are getting, and thus it will be a closed loop operation. In that way, this voltage source converter vector control is used just like in a induction machines vector control. Ultimately, there you from the encoder you sense the speed, and from these positions, from this, and here you sense the theta. The inner controller in turn determines the voltage difference of the converter in the DQ frame. So, hope you have understood it. Now, the inner current controller, that is ICC, shown in the figure here, see that how does it work, and it has a cross relations. So, you have ID reference, and this is essentially is a voltages in DQ frame, and ultimately you have to compare with the other voltages. So, what happened here, this point is your ID and this is your ID ref, and thus you get the delta ID, and that you feed it to the PI controller, and same way the IQ has to be multiplied with this term. This is a cost term, and ultimately you will add up and it had to be subtracted, and that will be your VD reference. Same way here IQ and it is IREF, you got IQ ref, you feed it to the PI controller, and same way ID will be multiplied as a cost term, then subtracted with it, and it will overall it will be subtracted from the IQ, and thus you get the VD ref, then you convert into the DQ to the ABC frame. So, what we can say that this inner current control, that is ICC in abbreviations, is shown in the figure 4 here, and usually comprises the first proportional PI controller. Its bandwidth has to be very high. So, it depends on the switching frequency. So, if you have a 10 kilohertz switching frequency, that means you will get around 100 microsecond. So, 100 microsecond, and we expect that within the 10 cycles you will actually compensate an error. Then your bandwidth required to be 1 millisecond. So, that will be quite first controller. So, the PI controller tracks the reference current that is set by the outer controllers and produces the voltage difference from the converter. Now, the PI controller tracks the reference current that is set by the outer controller and produce the voltage difference for the converter. So, the structures of the inner current controller of ICC at the point of common coupling, that voltage we will represent in the ABC frame at ES, and in DQ frame please see that in DQ frame will be ED and EQ, and the converter voltage as Vc. So, we can replace this, that is ES minus Vc equal to RL into IC plus LT dIdC, where IC is the current from the AC grid to the converter, and RT and the LT represents the equivalent resistance and the resistance and the inductance from the point of coupling to the pole of the inverter. And thus we can rewrite this equation. This is the cross term, this is the cross term, please go back to this. This is has been multiplied with the omega LT, and this has been multiplied the omega LT. So, this is the value of the VD RTD, and from there we have these two equations. Now, the voltage of the ICC is obtained as we have shown in the figure also in equation 2 and 3, and the reference voltage of VD and ID are being transformed and back into the AVC frame by the reverse transformation. So, thereafter we require to talk about the voltage source converter control in detail, and so that we will take you in the next class. Thank you for your attention. I shall take the next class from this point, that is the voltage source converter control, and how it will control this voltages, this power and the AC mains problem, that is drooping, and also the reactive power control. Thank you for your attention.